Hi class. In the first video from section 7.2, we defined the Laplace transform and talked about how to compute it. And in this video, I wanted to give a little bit of sort of theoretical information about when the Laplace transform can actually be proved to exist. So here's the definition again as a reminder. And we know that we might run into some problems because we have this improper integral. So, an integral is an area under the curve, and you can imagine that if you have some function that goes like this, and you're trying to add up all the area from 0 to infinity, that sometimes that area is just going to be infinite. So we need to make sure that when we're defining something that we're actually going to be able to say that this integral converges. So we're going to line up some properties that f is going to need to have, which will guarantee that this integral exists and is finite. So first I'm going to lay out a definition. This is the definition of a jump discontinuity. So that's a function defined on an interval, and um, we have a point in our interval where we stop being continuous, but we were sort of continuous everywhere before and after. So here's how this is going to look. Let's say we have our interval a to b and a point in the middle. And then we have our function, which is coming along. And then when we hit that spot, we stop being continuous, but then we sort of, continue on being continuous. So the limits, these one-sided limits, you've probably seen these in calculus before. So this is the limit as you approach t naught from the left, from the negative side, and then the limit as you approach t naught from the right-hand side. So those values, this one here would be the limit as we approach from the left. And then let's do another color. The one up here would be the limit from the right. There's a lot of T-shaped things here, huh? There we go. So it's a natural sort of concept where we're approaching from the left and we are getting close to this value, but that's not actually the value of the function. Where our value is up here, which is the same thing as the limit from the right. And the value might, you could even have this could be like an open circle, and then the value of f at t naught might be somewhere else. It doesn't really matter because that's a different concept than what these one-sided limits are. In any case, this is an intuitive concept that we have a discontinuity at t naught, but it's just a jump from, we're heading one place and then we jump someplace else and then continue on from there. And this is an important concept because you can imagine that if you were taking an integral, if you were integrating this function from a to b, this discontinuity wouldn't really matter. Like you can still compute the area under the curve. The value of the function at particular points, at like a single point, doesn't have any impact on the area. And so what I just said, I can sort of summarize in another definition, which I'll write it now. So this property, a function f is piecewise continuous if it's continuous at every point in a finite interval, except possibly at a finite number of jump discontinuities. And then it's piecewise continuous on the whole the whole half plane, whatever, from 0 to infinity, if it has only a finite number of discontinuities on any finite interval. Okay, so let me explain why a couple of these things are in here. So first of all, let's give an example of a discontinuity that's not a jump discontinuity. So let's say we have a function that goes like this. It's got like a vertical asymptote. So this is not a jump discontinuity. So we don't want any of those things. If it has something like that, then it's not piecewise continuous. And the reason we don't like this is that um, these left and right hand limits are not finite. They go to infinity. So if you were adding up the area under here, it would possibly be infinite, and we don't want to deal with any of that. That's not going to be helpful when we're defining our intervals or our integrals. And now this uh, concept of piecewise continuity on the whole right half of the number line, um, it's actually okay if we have an infinite number of jump discontinuities. For example, let's say that we have a jump discontinuity at every natural number. Okay, and so our function's maybe going to go like this. Let's define it like this. I don't know. I'm just kind of drawing some things. It doesn't really matter. So at every natural number, we're hopping back down. Okay, so this is piecewise continuous on 0 to infinity, even though it has an infinite number of jump discontinuities. Because any 0 to n, if we looked from 0 to n, it would be only a finite number of jumps. But then if we expand out to 0 to infinity, we have an infinitely many. However, if you had, let's say instead you had jumps at, I don't know, let's say you had one at 1 and at 1/2 and at 1/4 and at 1/8. And at each one of those, you have a jump. So it doesn't really matter what's going on outside of there, but let's say you're jumping up like this. And you're doing that on smaller and smaller things. So now we're going to have an infinite number of jumps on a finite interval. So this is not piecewise continuous because you end up accumulating too many jumps, and that's not going to let you, like in the limit, you're not going to be able to evaluate that integral that we want to do. Okay, so that's why we have some of those things here. Basically, we want a function to be continuous except at like a reasonable number of jumps where we have few enough that we can break it up and compute an integral. Okay, so we're definitely going to need our function f to be piecewise continuous in order to be able to compute this integral of the Laplace transform, right? Otherwise, there are just too many bad behaviors possible. But we need one more thing, because remember this example that I gave here. This, if this thing is growing too much, then the area under the curve is going to be infinite. So we need the function to be kind of small. But on the other hand, we are multiplying f in this definition by a negative exponential, or like a diminishing exponential. And so let's think about functions like that. So now I'm just sketching. Let's say we have, I'm not going to call it f. Let's call it g of t equals e to the, some alpha, negative alpha t for alpha negative, or alpha positive, sorry. Um, that is going to look like uh, this kind of exponential decay. So the area under the curve is going to decay fast enough to where the stuff out here is going to be negligible, and in the limit it's going to exist. And you could prove this. So then the integral from 0 to infinity of e to the negative alpha t dt is finite. And so we want the integral from 0 to infinity of e to the negative alpha t times f of t dt. Remember, that's the definition of our Laplace transform. We want this to be finite also. So we need this to be sort of small enough that it's not going to cancel out. So if f of t got really large and it sort of like overtook this exponential, like multiplying these together, we just need f to be like kind of smaller than an exponential, so that the f of t doesn't just make this whole integrand grow too large to be able to integrate it out to infinity. So let's put that down in a definition that really says what we mean. So here's our definition. A function f is of exponential order for some number alpha if there is some t and some m where your f in absolute value is less than this exponential function. And so the crucial thing about this is that it doesn't matter what's happening for a while. So you might have some function where anything is happening, like, we're not even saying that it's piecewise continuous. It can be, well, I mean, it's not looping around like that, but it's going crazy. But then at some point, and it can even be growing really, really fast, but at some point it settles down and is always going to be, well, now I want to make this thing smaller. Okay, so let's say at some point t, now there is an exponential function. So this is me to the alpha t, where now our function, even though it was going crazy and doing all this, whatever, now it's settling down and is always going to be smaller than our exponential function. So this is saying that in the limit, like out under here, this function f of t is controlled. Okay, so the red one is f of t. And so even though this one is growing really big, if we then multiply it by an e to the alpha t and do the Laplace transform, then it'll get small enough that we'll be able to take the Laplace transform and that integral will converge. So we'll see that in detail here in a second. And let's see an example of a function that doesn't have exponential order. So let's think about f of t equals e to the t squared. So this is not of exponential order. And we can see that by thinking about Remember, we're only concerned about what's happening as t gets large. So that's really in the limit as t goes to infinity. So think about e to the t squared over e to the alpha t. And this, we can sort of subtract the exponents, and we get e to the t times t minus alpha, right? Because that's t squared minus alpha t. And this limit equals, oops, not alpha, equals infinity. Because no matter what alpha is, this will always be bigger. You'll always get that t squared. So the other way you can think about this is equal to the limit as t goes to infinity, e to the t squared minus alpha t, or let's even do it this way, times e to the negative alpha t. So this goes to 0, but this goes to infinity faster. And you can check, like if you don't really believe that this one goes faster, you can check this limit with L'Hopital's rule. Because what L'Hopital's rule is doing is basically saying, well, which one is happening faster? And faster means taking a derivative, which is why you take derivatives at the top and the bottom. That's sort of why L'Hopital's rule works. And that's the intuition here. This is getting big faster than this is getting big, than this is getting small. And so as a consequence, if this is going to infinity, then this has to be bigger than the bottom. And it's never going to be controlled or bounded by just a e to the alpha t. So that's why e to the t squared is not of exponential order. Okay, so we have put some definitions into place, piecewise continuity and exponential order, because those are the things that we need to guarantee the existence of our Laplace transform. So here is our theorem. The two conditions we have on f, if f is piecewise continuous on 0 to infinity, and it's of exponential order alpha, then our Laplace transform exists for s greater than alpha. So what's with this s greater than alpha business? Well, remember when I was giving this example over here, and I was sort of talking about the definition of Laplace transform, I used an alpha, whereas the definition that we laid out before has an s. So the point is that if f is bounded by alpha, by an exponential of size alpha, like an e to the alpha t, then when s is bigger than alpha, this part will make the whole integrand small. As long as s is bigger, like if, I'm going to prove this in a second, but if f is sort of bounded by e to the alpha t, then e to the alpha t times e to the negative st will get small. That's the intuition if s is bigger than alpha. Okay, so that's the sort of the rough intuition, and I'm going to put that into math right now. So here's our proof. We need to show this. So we need to show that this integral, the definition of the Laplace transform, so that's what this is. This is the Laplace transform of f at s. We need to show that that converges. So we know something about f. We know it is of exponential order. So we know something is that it's bounded after some big T. So let's break up our integral into before T and after T. And this T is taken from the fact that f is of exponential order. So it's taken to satisfy that f of t, where did we go? That this definition of exponential order is satisfied. That's where that t comes from. So if we can prove that each of these two integrals is finite, then we will have proved that their sum is finite as well. Okay, so the first integral, which is this one right here, this one converges because f of t, and thus also e to the negative st f of t, are piecewise continuous. So that's on a finite interval, as long as your function's not shooting off to infinity or anything like that. If you're piecewise continuous, then you can calculate that area under the curve. So for the second one, we have an improper integral, and we're going to use a comparison test for improper integrals, which says that if the integrand is bounded by something, if there's some bigger function and the improper integral of that bigger function converges, then the improper integral of the smaller function will converge. So to say that again, because f is of exponential order, for t greater than t, we have that f of t in absolute value is bounded by this function, m e to the alpha t. And therefore, let's go back to black, the integrand of this guy up here is e to the negative st f of t. In absolute value, this is, well, we can say it's equal to, the exponential is always positive, so we can pull that out, e to the negative st absolute value of f. And now we can just, plug that in here. And this inequality is m e to the negative s minus alpha t, right? So if we can show that the integral of this thing from 0 to infinity, if that converges, then the integral of this will also converge. So the crucial thing is that we need to take s bigger than alpha so that this exponent up here will be negative. Let's see. So for s bigger than alpha, let's take the integral from big T to infinity of m e to the negative s minus alpha t dt. So we can do a u substitution here, and we get that this equals m over negative s minus alpha. Remember, s and alpha are like fixed values of e to the negative s minus alpha t. And we have to evaluate this from t equals big T to t equals infinity, where that evaluating on infinity is a limit. So this equals m over negative s minus alpha. So it's the limit as t goes to infinity of e to the negative s minus alpha t minus, now we can just plug, for this bottom one, we can just plug in t equals big T. So it's just e to the negative s minus alpha big T. But the whole point is that this, we've already seen this goes to 0. Because minus alpha is positive, so the whole exponent here, as t goes to infinity, that's always going to be negative, and that's going down to 0. And so the integral here is going to equal, we lose that minus sign, so we get m over s minus alpha e to the negative s minus alpha big T. And those are just numbers. That's just a number. So it's finite. So then, by the comparison test, which you can look up if my sort of rush description of it hasn't satisfied you. So by that, we get that the integral of this kind of smaller thing here, let's say of t to infinity of e to the negative st f of t dt is also finite. And so we have proved that both of those integral, or sorry, not those two, these two, the two on the right-hand side, that one there, are both finite, and therefore their sum, which is the one that goes from 0 to infinity, uh, is also finite. So then we get that, and that's the definition of the Laplace transform, equals the integral from 0 to infinity e to the negative st f of t dt exists. And that's it, we're done. That's the proof. So, and I guess I'll say for s bigger than alpha. All right, so that's proof that this definition that we defined for Laplace transforms exists as long as you have some certain fairly weak properties of f and t of t, and so that those apply to a large number um, of functions that we're going to see in the world, and that gives us a sound basis to be doing the rest of the theory that we're going to have for the Laplace transform.